record. All right, so recording is rolling. It is Friday, October 7th. You guys know today's the last day of the quarter, right? So this open notes take home quiz that I gave you guys before the hurricane, almost everybody's turned this in. Guys, if you don't have it in today, it's just got to go into zero, and I can't really do anything about that. So I got to have it by the end of today, right? If it's not in today, then that's all there is, because we're going into a 3-day weekend, right? Also, this form, one-on-one device agreement. You guys might have this. If you do, then go ahead and pop to the great trade at some point. This is, well, do within about a week, but next week's going to be a topic week. There's no school Monday. I'm not going to see you guys on Wednesday because you got a proctor exam. So sooner you get that in, the better. All right. Yesterday, actually last couple of days, we've been working on looking at this idea of centripetal force, right? Now, you guys know Newton's first law of motion says if something is in motion, it only ever wants to move in straight lines. So if something's speeding up or slowing down, there's got to be a force causing that acceleration. That's like a linear type acceleration. But then last couple of days, we started looking at, well, what about like changing direction? Because there must be a force that causes something to change direction if something's not moving in a straight line. Right? Like, what about like being on a curved path? In your Play-Doh bucket, there was the tension in the string was it pulling it in towards the center? Thinking. So, guys, which way do you think centripetal force always directs? Like this Play-Doh canister right here. Is there centripetal force pushing out or pulling in? Pulling in. Guys, does centripetal force always point to the center of the circle? Like a center-seeking force? Yes, it does. Because, again, if you cut the stringer here, wouldn't this want to fly off according to Newton's first law of motion just to a straight line path? So it's deviating from that path towards the center of the circle. That's what this dashed line is, like the actual, right? Is it? So center-seeking force, right? All right. Now, since we're getting into this rotational type motion, what if we saw a question like this? Could you guys imagine up in deep space there might be a cylinder shaped habitat? I'll call this an O'Neill cylinder, and see it's like rotating along this axis of rotation. You guys see all these people like standing on the inside ring, Okay. Usually about this time of year, I get questions about the movie Interstellar. If you guys have seen that, they had some O'Neill cylinders going on in there. Do you guys imagine if this thing is like rotating, that all these people might feel some kind of artificial gravity? Now, it wouldn't be real gravity. We've got to get to universal gravitation. Kind of an awkward way to in the week. If still got to tell you guys about universal gravitation, we'll save that for next week. But this could be like an artificial gravity. Like if this guy closes his eyes and the thing is spinning, it might be extremely hard to tell the difference between real gravity and like fake gravity. So it's some normal force from the wall that's providing us a centripetal force. I wonder how fast the thing has to spin. It looks like all I gave you here was a 20-meter radius. So if you know like the radial size of this, right, and say you have some target acceleration, that looks a lot like equivalent to Earth gravity, right? Let me flip my screen for a couple minutes here. Stuff still. All right, connect. All right, because I want to show you guys some video demos of exactly this going on. All right, so connecting. All right, here we go. All right, let me try this again. All right, share screen, share. All right, so to bring up another movie, does anybody know a movie from 1968 called 2001: Space Odyssey? Maybe? Yeah. So here's a top line special effects in the 1960s, which I think still holds up today. Of course, that's not really real, but that's what it would look like. Okay? In fact, the only reason we don't have something spinning like this in space right now is that it's really expensive to get stuff in space, right? So it's really just a matter of economics, right? Like, to transport something in space is like equivalent to like its weight in gold, like trying to move it. Right? Well, what would it look like inside there, like inside that thing? Right, so this isn't exactly supposed to be the same one, but it's the same idea, maybe like a smaller type version of this. Right, look at this guy like running around here. Okay. Again, this isn't real, it's from a movie, so he's not really in space, but it would look pretty similar to this. I think how they actually shot the scene was they created a giant cylinder. They had it like rolling around on the ground. They had a camera like fixed in one spot, just like, and the camera was like moving. Right? Okay, so that's kind of how they got the shot, but the idea is he's over there in space like running around. Right? Now, truth be told, if this were a true O'Neill cylinder up in space, it would be just a little bit too small. Do you guys think it's possible with this type setup that the gravity of his head and the gravity of his feet, again, it's not real gravity, it'd be like fake gravity. Okay? There might be too much of a difference, possibly, right? But maybe if it was a giant O'Neill cylinder, right, then it'd be really hard to tell the difference. We're about to address all that too. Let's look at here's kind of the mechanics of this, right? So if you have something rotating, suppose you're sitting in one of those boxes. Did I show this to you guys 2 weeks back? No, not yet. Okay. Suppose you're sitting in one of those boxes. Do you feel like you would be thrown outward? Okay. That's what you feel. Sometimes that's called a centrifugal force, but usually in a physics class, if you guys ever take physics in college, never use the word centrifugal. That's referring to like an outside seeking force, which is only apparent in a rotating frame of reference. Like if you're sitting in one of those boxes, you think you're being thrown out. But from our point of view, like from the camera's point of view, and an inertial frame of reference, right? One's not accelerating at all. You say, no. What's actually going on is the back wall is pushing and pulling that person like into a circle. That's a centripetal force, like a center seeking force. You guys get that idea? Let's go inside a second. I haven't shown you guys this either. All right, here, let's take a look. Right. So this guy's sitting in that box. Well, an equivalent one, right? Okay. You guys see the G counter up here? G's. Guys, how many Earth G's are we in right now? One Earth gravity. That's a different way to quantify acceleration, right? 9.8 meters per second squared could be equivalent to 1 Earth gravity, right? All right, so let's check this out.
Work hard. 3, 2, 1, engage.
How high is this going to go, do you think?
Take deep breath. You're on top. 3, 1, 2, 3. Top the shoulder. 3.
9 Earth gravities.
2.
So at that moment, he feels 9 times as heavy, right? Like his heart is pumping blood through his veins. It's all like 9 times as heavy as normal, right? That's about the max a human could take, but only for a few seconds. Like if they left him there like an hour, well, he'd be like flattened out, right? But if he's only there for a few seconds like that, and he's wearing a special suit, he's got through his training, so he knows like what muscles will squeeze. You see the guy shouting him commands him like squeeze your legs, blah, blah, right? Right, to get the blood flow.
Squeeze your leg, squeeze your blood. Hey. Keep breathing.
Last a few seconds, right? At 9 Gs.
See that? How you doing? How you doing? You know what happened? No. Huh? No. G-lock.
G-lock. There you go. Right, so, while I got this over here, let me show you guys an artist rendition of this. Oh, here's a pretty good one. Right. Come on, slide over here. There you go. All right, this could be like a cross section of an O'Neill cylinder. You guys see how it like curve around? Okay, and that one would be sufficiently big that if you're like walking around on one of those streets, it'd be like nearly impossible to tell the difference between that and like true gravity that's spinning, right? But I wonder how fast it has to spin, because if you spin it too fast, you guys just saw the video, you're gonna get too many G's, right? Right. But if it's not spinning at all, I bet you'd just be floating around, right? Okay. So, how fast does this thing have to spin? Right, so let's flip back over. Okay. And to address that, I really have to tell you guys about a new, sound it out, fix that. A different type of velocity that we haven't talked about yet, called angular velocity, also called rotational velocity or rotational speed. Okay. So you guys have turntables at your desk. So I've got as many as I can have. You guys got sort of group. Right. So you guys can get your hands on these and see for yourself. But say I got 3 Roosevelts here. Okay. I'm supposed to give this thing a spin. Okay. One Roosevelt's right near the center, one's a little bit far up, say, looks like about 7 centimeters out, one's about 14 centimeters out. Okay, so that's spaced out, right? It gives this thing a spin. Ooh, do you think if you pointed a radar gun at each of these Roosevelts, you get like a different linear velocity meters per second? Right. So how fast is the middle guy moving meters per second?
Almost 0.
Yeah, 0 or close to 0, right? It's close to 0. It's not right on 0. It would be 0, wouldn't it? Right? And then this guy is moving so many meters per second. Do you guys think that the guy on the far outside is moving probably twice the linear speed of the guy right here? I think so. I bet if you're twice as far away, you get like double the linear speed. Okay? But how about this? How about angular velocity? That's say like turns per time. You guys ever heard like revolutions per minute, right? RPM, revolutions per minute. Okay, so 1 revolution, that could be 1 complete turn. If this took 1 minute to turn all the way around, that would be 1 revolution per minute, wouldn't it? Okay. Now we're not going to use that unit very often in this class, but that's probably a concept you guys have heard of, right? Okay, so that has to do with like angular velocity, how fast is it turning? And these 3 guys, do they all are they all making the same number of rotations per unit time, the same turns per time? So do they all have the same angular velocity? Yeah. So they have three completely different linear velocities, but all the same angular velocity. They're all doing the same turns per time. Huh. Interesting. I wonder what the connection is between linear velocity and angular velocity. Oh, by the way, I got some new posters up on that wall that gives away the answer. But let's take a look at those posters. Okay. So I'm gonna go right to left, right, how those posters are hanging up on the wall. Okay. So let's start with this one here. Okay. Suppose this turns like some angle. I'm gonna label that angle theta. That's how we've been measuring angles more often than not in this class, right? Like theta. Okay. The amount that it turns, we can quantify theta. And I'm gonna call theta angular displacement. Okay. It's sort of analogous to x, isn't it? Like x could be linear displacement. In fact, if you're looking at a point on the edge here, follow this point. Can this point move some distance x? Notice I'm not saying displacement x, but distance x, like if you like walked around. Right. I bet there's a connection between these two, maybe something to do with this radius r too, right? We'll come back to that idea. Right. And angular displacement. One way you could, I could think of three ways to measure angular displacement. What's one way to measure?
Reads per minute.
Yeah, how about degrees? Yeah, degrees. Now, if you did degrees per minute, that would be like a angular velocity, which we're working up towards. But just the displacement itself could be some number of degrees, couldn't it? Right. What's another way to measure how far something's turned?
Radians.
Radians, and that's my favorite one for the math that we're going to do. Radians. Yeah. There's a third one that could be helpful too, which is what? Revolution. Yeah, revolution. Okay. So those are all ways to measure angular displacement. How about this? One revolution, that's equal to 360 degrees. Or I should have asked you guys that you would have said that, right? One revolution is 360 degrees. How many radians is that equal to? 2 pi. 2 pi radians. Okay. You guys remember the formula for circumference? Circumference equals 2 pi r. Ooh, that's about to link back to this x. X could be circumference if we go all the way around. So hold on to that idea because that's coming back. Okay. How about this? How fast is something spinning? Okay. And how fast it's spinning, I'm gonna refer to as let me box these in because as omega. So this Greek letter omega looks like a curly W. Okay. And so this is theta. This right here, I'm gonna call it omega. Okay. And this is angular velocity. You might hear it called angular speed or rotational speed. Right? That's how fast is it spinning. Do you think you could do degrees per second or revolutions per minute? You could do that, right? But more often than not, we're going to be doing radians per second. Okay. And then angular displacement, more often than not, we'll be measuring in radians. Right? And it'll make sense when we get to the equations why. Right? Okay. So yeah, anything to do with radians is the most equation friendly, right? Which you guys probably learned in a math class too, right? Okay. Hey, if I have an angular displacement and angular velocity, do you think at some point we're going to get the concept of angular acceleration? Something to do with like maybe this disk could be speeding up spinning, or if it is spinning, you let it go, maybe frictional forces could slow it to a stop, so it's like slowing down spinning. Right? And I'm going to refer to that as alpha. Right? Now you guys have seen this character before. Sometimes we use to designate angles, but in this context, it's going to represent. Okay, so alpha is what it's called. This could be angular acceleration. All right. Okay, right now space there. Right. And that could be in radians per second squared. Right. I bet you guys can imagine that, right? Is that true? Right. Good so far. Okay. Now, these what I boxed in, these are like rotational values, like angular values, right? How far is it turned? How fast is it turning? And something to do with like how fast is it speeding up or slowing down spinning, right? But you can connect these back to linear values also, and I sort of hinted that with this x, right? Like how about this? One trip around the circle is one circumference, right? And you guys know circumference equals 2 pi r. The 2 pi, hey, that looks like a measure of just one trip around the circle in terms of radians, doesn't it? Okay. In general, how far you've walked, x is equal to theta times r. Okay. As long as you're working in radians. Okay. Right, so if you know how far a disk is turned in radians, and you know, ooh, some radial distance from the center, right? You can multiply those together and say exactly how far you've walked around, right? So classic example, circumference equals 2 pi r, could be one trip around, right? Oh, how about this? What if, let's go back to this guy sitting right in the middle, right? How far is this guy moving in meters? Like 0 if he's right at the center, right? So it doesn't matter how, this thing could spin like 1,000 times. This guy's basically got nowhere, right? Because he has 0 radial distance from the center. So you have like I don't know, like 6,000 radians times 0 meters from the center, right? You're still gone nowhere, right? Hey, do you guys think you could continue this with these other variables and say how fast you're moving meters per second is equal to how fast you're spinning times your distance from the center? And do you guys think further that linear acceleration might be angular acceleration times how far you are from the center? Right? Okay, think you could do this? Right. Again, that's what that poster says on the right, hanging up there. Right? There's that new poster. Right. It's just this right here. Right. Now, again, you can only apply these formulas that I boxed in here if you're working with what unit to measure how far you've turned? Radians. Can you do degrees? Can you put degrees in here? Because 360 degrees, that's just an arbitrary Earth-based human thing that we came up with, right? Maybe something to do with the calendar is pretty close to 360 days a year. Maybe something to do with back in Babylonia, they used a base 60 system that they did it evenly. Oh yeah.
Would we want to do like the degrees over 360?
You'd have to convert first, right? Okay, yeah. Guys, how do you convert from? Suppose I gave you so many degrees, you have to figure out how many radians. How do you convert from degrees to radians?
Pi over 180.
Yeah, what 180 to pi is the conversion, right? Yeah, pi over 180 will convert from degrees to radians. Right. So suppose you have 360 degrees, and you want to convert to radians. Right. Now you guys know the answer to this one. That's why I picked this number specifically. You guys know it's going to come out to 2 pi radians, right? Okay. So I could say every 360 degrees is 2 pi radians, or you could use what Marcus said too. Is you could say 180 degrees per one. Pi radians. Right, degrees cancels. Right, get 2 pi radians. Same thing. Right. Hey, how about 1 radian? 1 radian. How many degrees is that? Does anybody know? We just how many?
180.
All right, let's try this.
180 over pi. Right?
Yeah, 180 over pi. 180 degrees every pi radians. Or again, you could do 360 over 2 pi. That would give you the same conversion, right? Let's see, what is 180 over pi? It's about 57 degrees. It's like 57.3 degrees. Okay. Hey, 57 degrees. That's pretty close to 60 degrees, isn't it? Which is a pretty special angle, right? So it's a few degrees short of that. Right. All right. So if you're wondering what is 1 radian, what the heck is 1 radian? Huh. Well, it's about that far. Right? That's about 57 degrees right there, right? Right. 1 radian. Right. There's pretty close to 6 radians and 1 complete revolution, right? But it's actually like 6.28, right? There's 2 pi radians. Right. All right. How about this? Let's do a little bit of kinematics. Right, we'll do a little bit now, and then this is gonna come back in the future. You guys remember those 3 kinematic formulas? X equals v naught t plus half at squared. You guys should definitely have these memorized by now. Although you could reference them on the AP equation bank, but it's a good idea to have these memorized. Okay. You have squared equals v naught squared plus 2ax. Okay, you guys remember those 3? Okay. Hey, do you think if you popped in rotational equivalents for every single one of these variables, you get 3 completely valid new equations? They go like this. How far have you turned in radians? Now, again, this has to be in radians for this to work. Right? That's analogous to x, how far you've walked in meters. How far you've turned in radians is omega naught t plus half alpha t squared omega final. This is how fast you're spinning. It's how fast you started spinning plus alpha times t. And then omega final squared equals omega initial squared plus 2 alpha theta. Right? It's if you just pop in the rotational equivalents of the linear variables, you get 3 new valid equations. Right? That has to do with like a rotating disk. You guys get that? It knows the variable that's the same. Time is the same. Time is still time, but everything else they just swapped out. Right? Theta is now, or sorry, x is now theta. V, so how far have you gone? How far have you turned? V is now omega instead of how fast meters per second. Now, how fast are you spinning? Right, the radians per second. And A is now alpha. Right. Okay, you guys good? Right now, last 2 days you guys have put together a formula that says centripetal force. Centripetal force is mv squared over r. Right, we've been working on that last couple of days. You guys figured this out experimentally, right? Through empirical data, right? But what about like a whole turntable, like a whole turn disk? And we're getting closer to this question. Okay, I'm working my way towards this right here. Okay. Some do with like a rotating platform. Maybe I'm not so much interested in V as omega, right? Because here's the question: how fast should this O'Neill cylinder rotate? That's another way to say is that what is the angular velocity? I'm asking you how fast is this thing spinning, right? Which is not exactly addressed here, but it's kind of getting towards that V. But this V is the linear velocity. See, what that V would address is like if I'm say on a space probe out here, just stationary, I'm watching this thing rotate from a third person point of view, and I point a radar gun at these people, then that would tell me what V is, right? Right. But you guys see this ladder right here? What if this person like climbed with this ladder, climbed up to the center? Do you think their V is constantly changing? Right. In fact, you know this. You know that the V is proportional to the radius. If you're right at the center, you have zero velocity. It doesn't matter how fast it's spinning. If you walk partway up the ladder, so you're halfway to the center, if you cut that r in half, you would have half the velocity for the same angular velocity, right? Half the linear velocity for the same angular velocity, right? All right, so let's do low substitution. Let's take this right here. Guys, is omega equal to v divided by r? Is that true? Omega is v divided by r. Is that okay? Okay, I'm going to do that right here. I say omega is equal to v divided by r. I'm going to take this expression and substitute it right there. Is that okay? Let's go right there. Okay. And let's see what happens. Just go to no. I'm so sorry, guys. This is the substitution. Oops. Okay, you guys tell me what I did wrong.
It should be in terms of V,
V is
W times R.
yeah, should be in terms of V. Yeah, okay, all right, you got it. Omega times R. Okay, oops. All right, so what I scratched out is totally wrong. You could say V is omega R. Oh man, I'm losing my mind. That's right? Okay, yeah, so omega could be V over R. Okay, no, we're good. Sorry, what I scratched out is perfectly fine. It's just not a substitution. Okay, oops. Okay, we're gonna substitute this in. That's what we're gonna do. Okay, so we're gonna substitute that right there. So centripetal force is m times omega R. Ooh, long week. Yeah, check it through. Right, so is that okay? Is that okay? Yeah. Right. Okay. So again, what I scratched out is an okay expression by itself. It's just not the substitution we were looking for. Okay. So V is omega R. Substitute that in there. Okay, so is this m omega squared R squared divided by R? And do a couple of the R's cancel? So we're getting centripetal force is m times omega squared times R. Right? Could that be true? So now you guys have two formulas for centripetal force. Right? You have the old one that you guys have been working on the last couple of days, pieced them together, which is this m times v squared divided by r. And now we have a new expression. Centripetal force is m times omega squared times r. Interesting, right? You guys see this? And so now you can know what centripetal force is just based on how fast is something rotating and also the distance from the center. Right? There's here's what I want to say too. I think I made this point yesterday already, but this is a really important point. Guys, centripetal force is never a force unto itself. It's always provided by one of the classic forces. So the last couple of days it's been the tension of the string, which was provided by the hanging weight. In the case of O'Neill cylinder, what's providing the centripetal force? the normal force from the wall. Isn't the normal force from the wall holding everybody in, right? And how about this? On your turntables in front of you right now, you guys take a spin, with providing the centripetal force, friction, right? So there's always some force that's causing that, right? You guys got good so far? So let's actually answer this question, and then we'll get to the pages on your desk. And so, how about this thing have to spin? Well, I've got centripetal force equals m times omega squared times r. Got that? Okay. Now, our target gravity field, again, this is artificial gravity, it's not real gravity. Right? We'll talk about that later. But we're looking for 9.8 meters per second squared. Hey, do you think that all these individual people have different masses? And this 9.8 meters per second squared, that has something to do with this, but it's not exactly it. I can't just substitute it because that's an acceleration and that's a force. What do I need to divide both sides by? M. Yeah, mass. Because I can have like 1,000 people in this thing and they all have their own individual mass. And this right here is the centripetal acceleration or the artificial gravity. Isn't this the artificial gravity right here? Omega squared times r. So maybe this is the actual form, that equation that I care about. Right, and we're trying to solve for what's the spin rate? How fast is the thing spinning in radians per second? Is that true? Okay, guys got that? Right, so let's solve in terms of variables. That's a good practice in this class. I see two algebra steps to isolate omega. What's the first algebra step? Yeah. Divide by r, right? Yeah, and then square root it. Right? So whatever the centripetal acceleration ends up being, divide by the radial size, take square root. That'll tell you exactly how fast this thing is spinning. Okay. So what should you sort of memorize or have its go-to formula? Maybe anything near the top of this page, but then you can just rearrange it, like solve for this, right? Oh yeah, go ahead. C, which stands for centripetal. Right? Yeah.
Why don't we divide by m again?
Okay, because this target question, we're looking for some target gravity field, like artificial gravity field around the rim. But you might have heavy people, light people. This force is measured in newtons, but the target acceleration is in that's an acceleration value, right? Right. So yeah, you guys remember if something's in free fall, all objects free fall at the same rate. Doesn't matter if it's heavy or light, because they have different forces and different masses, but the ratio of force to mass is just free fall gravity. Is that true? All right, so let's plug in these numbers. We know we're looking for 9.8 meters per second squared. Again, that's the acceleration that's caused by the normal force, and everybody experiences that same acceleration. As long as they're at the rim. If they start walking up the ladder, it's going to be a different story. But everybody that's equidistant from the center. And I gave you guys a 20-meter radius. There's 20 meters. They're on 20 meters. Is that okay?
Yeah.
Stick that. See what this is. 9.8 on 20. All right, so that came out to even number right there. Okay. 0.70 and what are the units? 0.70 what? Radians per second. Radians per second, because omega tells you how fast you're spinning, right? Radians per second. Okay, so we got this right here. That's actually the answer to the question, right? 0.70 radians per second. Now, I don't know, maybe it's kind of hard to imagine what that would be, or some of you guys can imagine that, right? Because 0.7 radian, remember I told you guys that 1 radian is about 57 degrees? So 57, right? So there's about 40 degrees per second. Can you guys imagine 40 degrees per second? What would that look like? That's probably pretty close to this, right? 40 degrees per second might be about this fast, right? So if this thing was 20 meters radius, and you were everybody's standing on the edge of the deep space, this is about how fast you have to go for you to feel like you're in one Earth gravity. Okay. How about okay? I know I put a page right there we didn't quite get to, but we'll have to stay up next week. Okay, yeah, that was really tough to wrap up right there. All right, so have we got any questions so far? All right, so next week we'll continue on this story and we'll do universal gravitation, and we're going to put it all together and get orbital speed. Okay, so we're going to do orbits next week. All right, make sure you got all your stuff turned in, and you guys have a great weekend.